All right, let's jump right into this explainer. Today, we're uncovering the invisible mechanics that dictate just how fast the chemical world operates. We're diving into chemical kinetics, which is this fascinating subject that bridges the gap between the random, chaotic collisions of microscopic molecules and the beautifully predictable mathematical formulas we use to actually understand them. You know, have you ever wondered why an iron gate takes literal years to rust, but if you mix an acid and a base together in a lab, bam, the reaction is virtually instantaneous? Thermodynamics might tell us if a reaction will happen in the first place, but it's kinetics that tells us how fast. So today, we are going to learn exactly why these speeds differ, and more importantly, how we can calculate and control them. So, here's our roadmap for today. First, the need for speed, then the collision model. After that, we're cracking the rate law, tackling the Arrhenius equation, and finally, decoding complex reactions. Let's kick things off with Section 1, the need for speed, and what actually drives a reaction. So, what exactly acts as the gas pedal for a chemical reaction? Well, take concentration, for example. When you crank up the concentration of your reactants, you're literally just packing more particles into the exact same amount of space. In a crowded environment, that guarantees more collisions. It is honestly just like adding more bumper cars to a rink. Moving right along to Section 2, the collision model, where we zoom in on microscopic chaos. According to this model, molecules act a lot like hard spheres that are just constantly moving around. But here's the catch. A reaction only happens if they experience what we call an effective collision. Most of the time, these molecules just harmlessly bounce off one another. For a product to actually form, the crash has to be absolutely perfect.
Right, so to be an effective collision, molecules have to smash together with enough kinetic energy to break their existing bonds. We call this energy threshold the activation energy, or EA. But wait, energy isn't the whole story here. They also have to be facing the exact right way when they collide. This is known as the steric factor, or P. And this strict orientational requirement, it is exactly why termomolecular reactions, where three molecules have to collide perfectly at the exact same split second, are incredibly rare.
Okay, let's transition into Section 3, cracking the rate law, where we translate all this physics into math. Now, this brings up a classic point of confusion, so let's clear it up. Remember that order is what you actually measure in the lab. It tells you exactly how the rate changes when you tweak the concentration. And yes, it can absolutely be zero or even a fraction. On the flip side, molecularity is pure whiteboard theory. It's literally just the number of molecules colliding in a single elementary step. Because of that, it has to be a whole number. I mean, you can't exactly have half a molecule colliding, right? Here is a fantastic shortcut if you ever get stuck on an exam trying to figure out a reaction's order. Just look at the units of its rate constant, K. For a zero-order reaction, the units match the rate of concentration over time. For a first-order reaction, it's just inverse seconds. It's such a simple trick, but it'll save you so much time. Next up, Section 4. It's time to face the ultimate boss of chemical kinetics, the Arrhenius equation. Okay, think about the number 30,000. That is a massive number, and it actually represents how many times a reaction rate can increase when you add a catalyst that drops the activation energy from 75 down to 50 kilojoules per mole, all at just room temperature, around 20 degrees Celsius. Just shaving a little bit off that activation energy barrier causes a literal exponential spike in the speed. It's mind-blowing. And the Arrhenius equation proves this mathematically. It shows us exactly how heat drives a reaction. As temperature skyrockets, it provides the juice, the energy needed to overcome that barrier. When that happens, the fraction of effective collisions basically explodes, and the reaction gets dramatically faster. Now, I know kinetics graphs can look a bit intimidating, but don't let them scare you. If you plot the natural log of the rate constant against inverse temperature, you just get a straight, downward-sloping line. It maps perfectly to that standard algebra equation we all know, y equals mx plus c. So if you can read the slope of that line, you can easily calculate the activation energy. Simple as that. All right, final stretch, Section 5, complex reactions, or as I like to call it, climbing the mountain. Let's do a quick half-life reality check here. The universal formula tells us that half-life is proportional to 1 over the initial concentration to the power of n-1, where n is our order. Because of this math, a first-order half-life just doesn't care how much reactant you start with, it's totally constant. Whether you kick things off with 100 grams or 10 grams, it takes the exact same amount of time to have. But for a zero-order reaction, the half-life is directly proportional to your starting amount. Keep that in mind because examiners love testing that conceptual difference. When it comes to complex reactions, I want you to think of a multi-step mechanism, like riding a bicycle up a mountain that has a few different checkpoints. Say you're doing a 10-kilometer climb. The first 5 kilometers to checkpoint X might be an absolute brutal incline, right? That's step 1, complete with its own massive activation energy. But then, from X to Y might be a nice, flat plateau with a way lower activation energy. The point is, each leg of the journey has its own unique hill to climb, its own rate constant, and its own speed.
And just like your overall time riding up that mountain is going to be heavily dictated by the steepest, most agonizing hill, the overall speed of a complex chemical reaction is entirely dictated by its slowest checkpoint. We call this the rate-determining step. If you want to speed up the whole reaction, you've got to find a way to lower the activation energy of that specific step. The fast steps, they honestly don't matter at all if the slow step is holding the whole show up. Okay, here's an advanced concept to really test your understanding. What happens to the Arrhenius equation if you push the temperature to literally infinity? Well, mathematically speaking, the exponent approaches 0, which means that entire exponential term just becomes 1. So at infinite temperature, the activation energy stops mattering completely, and the rate constant k simply equals the pre-exponential frequency factor, a. At that point, the reaction rate is completely temperature independent. How wild is that?
By the way, we've pulled all of these incredible insights, formulas, and analogies, from the math breakdowns to that bicycle analogy, straight from top prep sources like Collegiate Junior, just to make absolutely sure you are fully equipped to handle this material. So, now that you have the tools to translate molecular chaos into mathematical order, it's time to think a bit bigger. You understand the collision model, you can map out an Arrhenius graph, and you know exactly how to spot the rate-determining step. The real question is, how will you use this power on your next exam, or better yet, out in the lab, to actually control the speed of the chemical world? Keep exploring, keep questioning, and I'll see you in the next explainer.